Welcome back to CET3136C. This is Logic Devices Programming. In this video, we're going to discuss Chapter 5, which is Behavioral Style Combinational Design. The learning objective for this video is that you will be able to create a VHDL architecture using behavioral style combinational design. So let's talk about what that means. A behavioral style architecture uses algorithms in the form of sequential programs to describe a system. These sequential programs are called processes. So previously we've discussed the data flow style, and within that style we use Boolean expressions in order to obtain the output signals that we want. This is more algorithmic, and by algorithmic we mean using things like if-else statements, for loops, while loops, case statements, etc. So this is a more algorithmic approach to designing an architecture. So unlike data flow or structural styles, a behavioral style description does not imply a particular hardware implementation. It simply tells how the system is supposed to behave. So with the behavioral style, we're going to be learning about processes and how we can use a process to execute some sort of logic that we want to implement within our architecture. So the statement part of behavioral style architecture consists of one or more process statements. You can have multiple processes. Each process is a concurrent statement, but the statements inside the process are sequential. So you can have several processes, and each process will execute simultaneously. But what's happening inside each process is actually a series of sequential statements. They are executed in sequence, and their order is critical to their effect. So the order in which you write your statements within your process is important, because the statements inside of your process are not all going to execute at once. And in order to illustrate that, I'm going to start with a simple coding example of a half adder, which we've seen before, but this time, instead of implementing the half adder as a data flow style, we're going to implement it as a behavioral style. All right, so I'm in Quartus, and I'm going to start a new VHDL file within a project. I'm going to call my entity half adder. I have two inputs, A and B. They're both going to be standard logic inputs, and my two outputs. There's my entity declaration. I'm going to name this architecture 2 processes, just because that's what I'm going to implement inside of this half adder architecture. And then I have the word begin. After the word begin, I'm going to illustrate 2 processes. I'm going to begin with a label. You don't have to give your process a label or a name, but it makes it easier for debugging later, especially when you have multiple processes. So I'm going to call the first process P1. To begin our process, we have to use this keyword, process. And what follows is a sensitivity list. So this right here is a sensitivity list that is going to have a list of signals that are going to cause your process to execute. So for this process, I am going to calculate the sum output of my half adder. In order to calculate sum, I need to know what's happening with both inputs A and B. Sum depends on both of those inputs. So I have to include these 2 signals in my sensitivity list. So once I have listed the signals that I want the process to respond to in the sensitivity list, I'm going to say begin. Sum gets A XOR B. And that's the end of my process. All right, so this is my first process where I calculate the sum. My second process, I'm going to call P2. Again, I'm going to start with that keyword process, and then I have my sensitivity list, which describes what the process will respond to. We have the word begin. And now I'm going to write the equation for carry out. Carry out gets A and B, and process P2. And that's the end of my architecture. So, a few notes about using a process. Remember that a process in its entirety is a concurrent statement. So process P1 and process P2 will execute at the exact same time. The statements inside the process are sequential. What happens after this word begin is going to happen in a sequential order from top to bottom. So you do want to have think about precedence or priority if one event should occur before another. Once you get inside of that process after the word begin, everything is a sequential statement. But the two processes that I've written here will execute at the exact same time. In this example, I have two processes that are independent of each other because each is sensitive to input port signals and not to a signal assigned a value by another process. So both of these only depend on the inputs to my entity themselves and not from the result of another process. Sometimes one process will have to execute an operation based on the signal or the output that is produced by another process, and those are called dependent processes. And in that case, those processes would have to communicate with one another. Let's say that in a different world, carry out had a dependency on what sum was going to be. Then these processes have a dependency. For our example, these processes are independent because sum and carry out only depend on A and B. They don't actually depend on the output of another process within your architecture. So we call these independent processes. So when you have a process, it may represent the behavior of all or some portion of a design. That sensitivity list is going to, again, describe the signals that will execute the process. So if there is an event on A or B, and an event is a transition from high to low or low to high. So if there is an event on input A or input B, this process will immediately begin to execute. When it is, once it executes the code that's written here, so once sum is going to get its signal based on A XOR B, then that process is going to be what we call suspended. So basically that process is going to be like in a waiting state or a sleep state, and nothing will execute until there is another change on the two input signals A and B. So that sensitivity list is very important because if you expect a signal or some value to change based on an input, you need to list it in your sensitivity list. So for example, if I took B out of my sensitivity list here, the sum is only going to change whenever input A changes. It won't change whenever input B changes, even though I have it right here. This process is only going to execute based on an event on whatever signals are listed on your sensitivity list. So if you expect your process to execute based on a change in A or B, they both need to be listed here. So when we think about a process, it can be viewed as an infinite loop whose execution is repeatedly suspended and resumed. So the sequential statements in a process are executed first to last, then back to the first. A process continues to execute its sequential statements until the process is suspended. If your process has a sensitivity list, it will automatically suspend after the last statement in the process is executed. So in our case, we have a process with a sensitivity list, which means once an event happens on signal A or signal B, this code will execute and then the process will automatically suspend itself. If you have a process that does not contain a sensitivity list, which is very possible, you could have a process that's going to execute some function that isn't dependent on your input signals here. So you may not have a sensitivity list. Then you'll have to use the idea of a wait statement to cause the process to suspend so that it won't run indefinitely. So if you don't have a sensitivity list, you need to use what's called a wait statement, and then the process resumes execution when the wait statement's conditions are satisfied. So you can tell it to wait until something happens before executing again. That's the wait statement. Okay, I'm going to save my file. Just going to call it half adder. And I'm going to check for errors. And everything looks good. So this is just the introduction to how we use a process, and this is the general idea behind a process. Now in our case, we only had one line within our process, one actual piece of code that accomplishes something. But your process can be many lines. It can have a number of things that you can accomplish within one process. And you want to be careful to sort of organize your processes based on what you want to accomplish. So this is one method of implementing processes. It's not the only way to do a half adder using processes, but this is an introduction to the behavioral style. And anytime you're doing behavioral style, you're always going to have processes followed by an algorithmic approach to implementing a piece of code. So next we're going to look at some of the tools that we can use within a behavioral style architecture. The first thing that we're going to look at is a case statement. And to do that, I am going to design a 2 to 4 decoder using a case statement. So I'm going to just start a new VHDL file here, and I'm going to copy and paste my library statement and begin my entity. I'm going to call it 2 to 4 underscore decoder. And I'm going to use case because I'm using case statements to describe this particular architecture. I'm going to do it a second way using something else. So I'm using that word case to differentiate this piece of code from the next piece of code. So with a 2 to 4 decoder, we're going to have two inputs, A and B, and we're also going to have an enable called G bar. Remember, G bar is that word bar signifies that that's an active low enable. So here's my inputs, and with a 2 to 4 decoder, I'm going to have 4 outputs. I'm going to call those Y0, Y1, Y2, and Y3. Now I'm defining these as out standard logic, but you could easily create a standard logic vector for those inputs and outputs if you wanted to as well. I wouldn't recommend it so much for the inputs, but for the outputs, since we just have 4 outputs coming out of our decoder, this could also be defined as standard logic vector with a size of 4. So I'm going to end my my entity right there, and then I'm going to move on to the architecture. That word did not turn blue, which is an indication that I spelled it wrong. I'm just going to call this architecture behavior. And now I'm going to begin the architecture. I'm going to start with a process. For that process, I'm going to call it case statement. And for this process, My sensitivity list is going to be A, B, and G bar. Basically, I want this process to execute anytime there is a change or an event on any of my inputs, A, B, or the enable. And then I'm going to begin. I'm going to start by assigning a default value to my outputs. All right, so that's my default value. Notice that if I want to assign a default value to a type standard logic, that means I'm assigning a 0 or a 1, and I have to do that with single quotes. So I'm assigning right now all of the outputs to be high. Now this decoder is going to have active low outputs. So right now, what we're setting here is the inactive state for the outputs. And then I'm going to add a case statement here. So here's my case statement. I'm going to do the word case. I'm going to typecast my 3 inputs into a vector. Typecasting those 3 inputs into a vector where G bar is the most significant bit and A is the least significant bit. And here's how I'm going to write my case statement. All right, so we have case, standard logic vector, apostrophe, G bar, comma B, comma A, is, and then we have the word when. When 0, 0, 0 corresponds to the standard logic vector we just created. So when G bar is a 0, B is a 0, and A is a 0, that means output 0 should be active. So we're going to take output Y0 and cause it to be active by storing a 0 in that particular output. We're going to continue this by covering each case for the inputs A and B as long as G bar is low. So if G bar is low and then the inputs are 0, 1, well now that means output Y1 is going to be active. And this is the syntax we're going to use to make that happen. That's the end of my case statement. So I'm going to end it with that word end case. I'm going to end the process right here and end the architecture. So with this case statement, what we've done is we've said when G bar is low, so the first value in each one of these when statements is 0. So when G bar is low, we're going to look at our 4 possible inputs of A and B. And then we're going to activate one of the outputs based on that combination of inputs. Let's say that none of these cases happen. So when others means when any other input combination occurs between G bar, B, and A, when any other combination occurs, we're going to assign a value of null, which basically means take no action, do nothing. And if we've done nothing, that means essentially that our default assigned values are what we're going to see at the output. So that means if the decoder is not enabled, we'll see all ones. Once the decoder is enabled, we'll see one of these outputs become active based on the values of B and A. So this is one way to implement a 2 to 4 decoder using a case statement. And there's the syntax right there for a case statement. So I'll save this. And check for errors. No errors, we're good to go. So then you can functionally simulate this and or program it onto the Max 10 board, manipulate your 3 inputs, A, B, G bar, and notice that one of your 4 LEDs should be low depending on which input is depending on which inputs you've activated. So that's the first way we're going to implement a 2 to 4 decoder using a case statement. We're going to implement this a second way using some if statements. Now, if you've taken any other programming course in the past, then you're pretty familiar with an if statement. We're going to go over the syntax that you need to implement an if statement within a behavioral architecture. So that's our next example. So I'm going to go ahead and copy and paste what I currently have into a new file, and then I'm going to make some changes. So here's my new file. I'm going to change the entity name at the end. Instead of calling it case, I'm going to call it nested if, because I'm going to show you what a nested if statement is. Our inputs are going to be the same, and our outputs are going to be the same. We're just changing the architecture. So I'm going to update the entity with the new name, nested if. Everything here stays the same. In my architecture, I'm going to update the name here as well. And then I'm going to begin with the architecture here, and instead of naming it case statement, I'll call it nested if statement. And our process is going to respond to A, B, and G bar the same way it was before. We're going to keep our default output values, but now, instead of using a case statement right here to implement our logic, we're going to use if statements. So with a decoder that has an active low enable, we can't really respond unless G bar is low. So we're going to write an if statement check that status. If G bar is low, then we're going to decide what else to do. So with this particular decoder, if G bar is low, we then need to decide what to do based on the values of A and B. So if G bar is low, then next we're going to look at A and B. If B is low, and A is low, then here's where we want to activate output Y0. We want that to go low. Y0 gets a low. So we're going to check G bar first. If G bar is low, then we're going to come to the next line and execute that next line. If this statement is not true, everything that happens after it will not occur. Nothing will occur if this statement is not true first. So if this statement is true, next we're going to evaluate this statement. If this statement is true, so if B is low and A is low, then output Y0 will get the value of low, so that that output is active based on the rules for a decoder. So if A is not low or if B is not low, then this statement will not happen. But what we want to do is evaluate some other ideas. So maybe A and B both aren't low. Maybe A is a 1 and B is low. We want to check for that scenario. So we're going to use what's called an else if statement. So if this is not true, we will then evaluate the next condition listed after else if. So if this or else if this. This is the next line we're going to evaluate. So we're going to now check for B to be low. And we're going to check for A to be high. So if B is low while A is high, that means that output 1 should be active. Else, we want to check to see if it's the other way around. If B is 1 while A is low, so I'm just going to actually copy this. If B is 1 while A is low, then output 2 should become active, so it's going to go low. And then lastly, we want to check to see if they're both 1. If A and B are both 1, output 3 gets a 0 and will go low. So we're going to call that the end of our if statement. We've checked each case. Assuming that G bar is low, we want to know if A and B are both low, if B is low while A is 1, if B is 1 while A is low, or if they're both high, and then take action accordingly. So with this if statement here, we have if, and then we're going to be checking to see if G bar is low. If G bar is actually low, then this is going to execute. Now notice this is a statement here where only one of these things can occur. If B is 0 and A is 0, then we're going to take this action. Or else, if B is 0 and A is 1, then we're going to take this action. Only one of these things is going to occur within your if and else if statement here. Now, for every if that you start to type, every if needs an end if. Only the ifs, not the else ifs. So I don't need 1, 2, 3 end ifs for each one of these else ifs. I only need one end if statement right here that corresponds to this if. Since I've started another if statement above that, I need a second end if statement right there. That's called a nested if statement, an if statement within another if statement. So that's what we have right here. If you didn't have multiple conditions to test within this if statement here, you could just have an if, like let's say I'm going to ignore all of this down here. You could have an if and then an else. Okay. So if you're only testing one particular thing, if B is low and A is low, then output 0 should be low. Else, so if any other statement occurs, you can have an else without the else if, and you could say, well, y2 gets, you could have whatever you wanted right here to happen. So it's like, if this one condition occurs, then do this, or else if that one thing doesn't happen, then do this. So you can have an else statement. You also can have an if without anything after it. You could check for this one thing to occur, and if this statement isn't true, you're basically going to take no action. You can just end if right there. You don't have to have the else. You don't have to have the else if. It all depends on what you're trying to evaluate and if you have multiple things you want to evaluate within a single if statement. So that's some options that you have when using an if statement. So I'll put my code back. So remember, this statement right here is a nested if because it occurs inside of another if. Every if must have an end if to complete it. If you don't have that end if, you will get a compile error. So that completes my architecture for the 2 to 4 decoder using a nested if. Again, if you're going to use an if statement, that's a behavioral style. So you have to put that within a process. If you write a data flow style architecture and you try to use an if statement without first putting it within a process, you will get an error. So that's a behavioral technique. So you have to use a process in order to use an if statement. So I'm going to go ahead and save my work and check for errors. All right, no errors. So there's our if statement. So we've talked about the idea of a process. We've talked about the case statement. We've talked about the if statement. Now let's talk about writing some loops, like a for loop. That's what we're going to do next. So for our next example, we're going to design a magnitude comparator. The magnitude comparator has two inputs. Each input is 4 bits long. It's going to compare those two inputs, and it's going to determine whether the first input is greater than the second, the first input is equal to the second, or the first input is less than the second. So we'll have 3 outputs, and one of those outputs will be active to describe the relationship between the two inputs, greater than, equal, or less than. That's a magnitude comparator. Again, another digital systems 2 concept that you should have discussed. Feel free to pause and go review that if you need to. And we're going to design this magnitude comparator using variables. So we're going to introduce the idea of variables. We're going to introduce the idea of a for loop. We're going to also introduce the idea of the exit statement within your loop. So I'm going to begin with another new file, just a VHDL file within my project. I'm going to go ahead and copy paste my library statements. I'm going to call this entity mag_comp for magnitude comparator. For my inputs, I have 2 inputs. I'm going to call them P and Q. In standard logic vector. 4 bits in size, so I'm going to have 3 down to 0. So I have 2 4-bit inputs, P and Q. For my outputs, I'm going to have P_GT, that stands for greater than Q, and that's an active low output. P_equal to Q, that's also active low. P less than Q, active low. All right, so there's my port statement with my 2 inputs, P and Q, standard logic vector, size 4, and then my 3 outputs, they're all active low outputs, P greater than Q, P equal to Q, P less than Q. And then that's going to end my entity declaration. And now I'm going to write my architecture. All right, so I'm going to write a process called comp. That process is going to respond to a change in P or Q. So I'm going to start with that process. And before I hit the word begin, I'm going to define a variable. So in order to declare a variable, I have to use the word variable. And then I'm going to give my variables some names. So we'll call this one greater. We'll call this one equal. We'll call this one less. And they're all going to be standard logic. So these variables are going to represent the idea that P is greater than Q, P is equal to Q, or P is less than Q. P is always going to be our first input. Q is always going to be our second input. I'll even add a comment in there to remind myself. So I have these variables. There's some differences between a variable and a signal. So for example, these are signals. These are my inputs and my outputs. These are signals. A variable is only visible within the process in which it is declared. So this variable here only exists within my process called comp. Once I go outside of this process, the value of any of the variables I've created here is not visible anywhere else. It's like your other processes or the rest of your architecture won't see it. It's like a local value that's local to your process. A signal is visible to all processes in the architecture in which it is declared. So my signals, P, Q, and then my output signals are visible everywhere. A variable is only visible within the process that it has been declared. That's the biggest difference between a signal and a variable. So a variable is great when you want to hold a temporary value that's only going to be used within a process. If you're going to be creating values that have to communicate between processes or between architectures, you're not going to want to use a variable. So it's a local concept, and the value of greater, equal, and less is only visible inside this process, nowhere else. So that's what a variable is going to be used for. So I'm going to continue with my process by writing the word begin. And now I'm going to start the process. I'm going to start by giving some default values to my outputs. So these are my default values. I'm going to go ahead and write a comment. And now I'm going to introduce the concept of a for loop. So a for loop will run for a certain number of iterations. You will decide that number of iterations. You're going to define the number of iterations by writing the word for. We're going to create sort of like a local variable I. That stands for index. We're going to write the word in. And we're going to say 3 down to 0 loop. That means I is going to start with an initial value of 3. Every time the loop executes, it will execute whatever code you've written after it, and then it will decrement I until you get down to 0. So the fact that I've written 3 down to 0 means this loop will run 4 times. It will run when I is 3, it will run when I is 2, it will run when I is 1, it will run when I is 0, and then once I becomes out of the bounds that are determined here, your loop will cease to execute. Your loop will stop. So you can have 3 down to 0. You could also do 0 up to 3. You can go 0 to 3. So you don't have to count down. You can also count up within a for loop. We're counting down in this case, and I is now a variable that I can reference as I'm, going through my execution of this loop. I is a value that I can reference. So what we're going to do is look at the most significant bit of our inputs. So that's going to be P sub I, because the first time I run this loop, I is 3. So the very first time this if statement is executed, we're looking at P sub 3. P is a standard logic vector 3 down to 0. So that's the most significant bit, the first bit in our value for P. We're going to compare Q and P bit by bit to determine which one's bigger. So the first thing we're going to look at is P sub I, and the very first time this loop executes, that means we're looking at P sub 3. We're going to see if that's a 1. We're also going to see if Q sub I is not a 1. So what we're looking at here, as an example, if P is 1, 1, 1, 0, and Q is 0, 1, 1, 0, well, looking at the first bit of P and comparing it to Q, P is bigger automatically. I don't even need to look at the other bits. I know as soon as this condition is true, P is bigger. And if P is bigger than Q, oops. If P is bigger than Q, then my variable greater is going to get the value of 0. Remember, we're using everything as active low. So greater is a 0 because this statement is true and P is greater than Q. 0 means it's active low. So our variable greater is going to get the value of 0. Once I've assigned that value of greater as being 0, and notice how I assigned it. I have a colon equals. This is how we assign values to variables. So signals get assigned a value using the caret and the equal sign. Variables get assigned a value by using a colon and an equal sign. So we're assigning the value of 0 to greater. Once we've determined that P is greater than Q, we don't need this loop anymore. We don't have to continue going through the loop. So I'm going to write the word exit. Exit immediately kills the loop. You immediately drop out of the loop if you hit the word exit. So if P sub I is a 1 and Q sub I is a 0, P must be greater than Q. We're going to say that this variable is going to go low, and then we are going to drop out of the loop. But what if this isn't true? So we're going to do else if. What if it's the other way around? What if P sub I is 0 and Q sub I is 1? What do we need to do now? Well, in this scenario, let's say that we're at the beginning of the loop. This is the first iteration, and P sub 3 is a 0, while Q sub 3 is a 1. Well, that means that P has to be less than Q. So we're going to say our variable less gets the 0, because P is less than Q in this instance. So we're going to assign that value to our variable, and then once we've determined that P is less than Q, we can exit the loop. So these are our two things we're checking for inside of the for loop. Basically, we're looking to see who has the most significant, who has the bit that's larger, and we're going bit by bit to determine that. So we're going to start at the most significant bit. So the first time through this loop, I is 3. If neither one of these two things happens, we're going to execute this loop again. So end the loop, we're going to say end loop. So that means I is going to begin at 3. If this is not true, none of this will happen. If this statement is not true, none of this will happen. And when we hit the loop, we go back to the top. I is decremented from 3 down to 2, and this executes again. So if P sub 2 is equal to a 1 and Q sub 2 is equal to a 0, then P is greater than Q. So we're going bit by bit, checking to see which bit is bigger, the bit in P or the bit in Q. So we're going bit by bit, and the reason why we have to go bit by bit is, for example, let's say that P is 0, 0, 1, 0. Let's say that Q is 0, 0, 0, 1. So when the loop executes, I is originally 3. We're going to be looking at P sub 3 and Q sub 3. Neither one is bigger than the other, so then I will decrement to 2, and then we'll be looking at P sub 2 and Q sub 2. Neither one is larger than the other, so then I will be decremented down to 1, and then we'll be looking at P sub 1 and Q sub 1, and right there we'll see that P must be bigger than Q. So we're going to check bit by bit until we hit one of these two scenarios. What if we don't hit either one? What if we don't hit either one? If neither one of these scenarios occurs, so let's say that the for loop begins, I starts at 3, we go through the loop once, neither one of these things occurs. I goes down to 2, we go through the loop again, neither one occurs. I goes down to 1, neither one occurs. I goes down to 0, and neither one of these conditions occurs. That means that P is not greater than Q and P is not less than Q, which means P is equal to Q. So after we exit the loop, we're going to verify by saying if, actually we don't need an if, we're just going to say if we get out of this loop and neither one of these conditions has occurred, we're going to say equal gets 0. And if you look at the code here, what we really want to do is actually change our assignment defaults not to be the signals themselves, but to be our variables. That way, they're all defaulted to be 1. And greater will be changed to a low if P ends up being greater than Q. Less will be changed to a low if, sorry, forgot this. These are variables, so we have to change the way we assign values. So here's our default values. Greater gets a 1, less gets a 1, equal gets a 1. So we'll start with these all being 1. If P ends up being greater than Q, greater will be changed to a 0. If P ends up being less than Q, less will be changed to a 0. If neither one of these happens, we need to make sure that equal is changed to a 0. And just to ensure that nothing has fallen through the cracks, we can go ahead and put an if statement here that checks to see that greater never changed, and that less never changed. So if greater is a 1 and if less is a 1, that means these two numbers that we're comparing must be equal. So we'll check that at the end, even though if this condition never occurred, greater still has to be 1. If this condition never occurred, less still has to be 1. But just to be overzealous, we'll have this if loop here to check and make sure. Greater has never been changed and less has never been changed. Therefore, the two numbers must be equal to each other because neither one is greater or less than the other. So now that we've determined what the two values are, how they relate to each other, we're going to store, or we're going to assign variable values to our ports, to our output ports. So our outputs were right up here. I'm just going to copy these. All right, so our greater than output port will get the value of greater. Our less than that's equal. Our equal output will get the value of equal. And our less than output port will get the value of less. So we're going to take our variable values and assign the value that's stored in this variable to an actual port. If we don't do that, our work here, remember these variables are local, they're inside the process. Outside of the process, our entity doesn't have access to the values of greater, equal, or less. So we have to assign those values back to one of our ports when we're done with the process. So we now we're going to end the process here. We called it comp, so we'll end that process. And then we're going to end our behavior. So now that I'm done typing up my architecture, before we compile it, there are two errors. I'll tell you right now, there's two things I intentionally skipped. I want to know if you found them as we were going through the code. If not, take a look, try and figure out. There's two errors. I'll give you a second to think about it, and then I'll tell you where they are. All right, so the first error is right here. Every if needs an end if. Without that, you'll get an error. Also, every if statement needs a then at the end of it. Without that, you'll get an error. So those are the two errors in this particular piece of code. It's going to happen all the time. I want to teach you how to identify your errors. You're not always going to remember every semicolon, every exit, every end if. It's fine. But the main thing is to be able to figure out how to fix your errors. So those are the two errors in this particular piece of code. And now if we create a symbol file, it should compile. So it does. And now we'll go ahead and do a functional simulation of this particular piece of code. So I'm going to create a new symbol file, not symbol file, schematic diagram. I'm going to go ahead and add magnitude comparator. P and Q are vectors. So if you're wondering how do I name this, if you double click it, it tells you what to do for a bus, meaning a vector. So for example, name hard bracket 3 ... So we're going to call this input underscore P, and since it's a vector of size 4, we're going to name it that. It should be named the same way it was defined in your port statement. In the port statement, it was 3 down to 0. So we're going to write 3 ... and hit OK. And then we're going to call this input underscore Q 3 ... hit OK. And these should turn a thicker color once you define them as a vector. Since that didn't happen, I'm going to reconnect these. See, it's thicker. If you have a vector and you named it properly, and if you connected it properly, it should look like that when you connect it on your BDF diagram. So I'm going to connect my outputs here. And give them all a name. All right, so I have my outputs, P greater than Q bar, P equal to Q bar, and P less than Q bar. I'm going to go ahead and save this, and my project was just called Chapter 5, so I'm going to save this as Chapter 5. Make sure whatever your BDF file name is matches your project name for however you created this, and then I'm going to go ahead and compile it. And I'm just going to hit pause and come back when this is done compiling. Alright, so I'm back and my compilation was successful, so I'm going to go ahead and start a new waveform. I'm going to go to the node finder and add my nodes. Notice that the nodes can be individually placed, or you can have a group. So I'm going to go ahead and put P as an input group, Q as an input group, rather than adding them bit by bit, and then my 3 outputs. Alright, so I have my outputs. I'm going to put greater than on the top, equal than, and then less than on the bottom. I'm going to give input P an arbitrary value. So if you go up here to this toolbar, click the one that says arbitrary value, and I'm going to give P the value 0110. I'm going to give Q an arbitrary value of 1110. And I'm going to give the outputs an initial value of high. And one of these will go low once we simulate. So I'm going to go ahead and hit run simulation, yes to saving my changes. All right, and if we look at the outputs here, here's our outputs. According to the arbitrary values I assigned, P is less than Q, which means that output should be low, and that's this value right here. These two are high. Notice the bolder bars. That's the high they initially started out with. And the output for P is less than Q is now low. So we can see that our functional simulation is verifying that our results are correct. So that's a little bit of an introduction into the behavioral style combinational design. Make sure you're reading the textbook for more information and more tools that you can use when implementing a behavioral style design. Be sure to read the directions in your labs for when you're able to use behavioral style, when you are able to use it. Experiment with for loops, experiment with if loops, experiment with case statements. Try to figure out how to make your logic more algorithmic when it suits you. These are just a few of the tools you can use. And that is the end of this video.